Hello everyone, I am Dr. Ritish Kumar. Today I will discuss the topic of some passive devices, microwave passive devices such as Magic Tee, hybrid ring and directional coupler. So waveguide tees we will discuss here. So first one is we have in the laboratory we have seen the E-plane magic E-plane tee and H-plane tee. So how we can define the E-plane tee and H-plane tee? So first we need to see the structure of the waveguide tee. So this is the side view. This is the side view of the waveguide. Here we can see here. Now this one is side view for the H-plane tee. So in the E-plane tee, we need to observe the electric field orientation of within the tees. So here we find that for the fundamental TE10 mode, for the fundamental TE10 mode, the field always be perpendicular, or we can say the field oriented either in the upward direction or in backward direction, downward directions as well. So in the case of E-plane T, we can say this is the side view of the waveguide. Here we can see clearly observe here the field is going downward direction. This is downward direction, like this. So here this arm is known as main arm or main waveguide, we can say, and something is extra attached to this main waveguide, that is a secondary waveguide, we can say, and in other terms we can say this one is the auxiliary arm. And how we can decide this one is E-plane T? First we need to understand the basic concept of it, because as we know the field is directed towards the downward direction. That's why this plane is known as E-plane. And this plane is known as perpendicular to this plane is H-plane. So this arm, we can say this arm is parallel to the direction of E fields. So that's why we can say if the secondary arm, that is auxiliary arm, if it is parallel to the direction of E-plane, then we can say this one T is known as E-plane T. And whatever we have observed in the case of E-plane T, just we can say the complementary we have in the case of H-plane T. So similarly, because this arm is the auxiliary arm, because here we can say this one is the main arm and this one is the auxiliary arm, as we have seen here. Now because this auxiliary arm is parallel to the direction of electric field. In other terms, we can say it is perpendicular to the direction of E field as well. So in that condition, we can say this secondary arm, auxiliary arm, is attached in the H plane direction, in the H plane. So we can say this one is this T is known as waveguide T. The main motto of this waveguide T is, because here two ports we have defined. The first port we can say this one, if we say this one is first port, if this one is first port and this one is second port. So if we deliver the power from this first port and second port, so obviously this power is combined to the combined at this junction, and we received the power at port number 3. Similarly, in reverse way, we can say if we deliver the power from port number 3, we can have the split of power in two directions, either in the port number 1 and port number 2 as well. So we can say this device can act as a power combiner in the first case, and in the second case, if we deliver the power at port number 3, it will known as a power divider. Similarly, we can say for the H plane T. So if we deliver the power at port number 3, we can have the power at port number 1 and port number 2, obviously. And if we attach two source at port number 1 and port number 2 simultaneously, so we can get the power at port number 3 with the summation of these two port power. So we can say these device can act as a power divider and power combiner as well. Now the thing is there can be two cases we can have in the case of E plane T and H plane T as well. So first we will discuss the E plane T. So in the case of suppose in the case of if we deliver the power at port number 2 and port number 1 and port number 2 simultaneously, if the power is in the opposite phase, so if the power, suppose if we deliver the power at port number 3, so we can have the power in the port number 2 and port number 1 as we discussed in the last slide. And similarly, if we apply the if we apply the input at port number 1 and port number 2, we can have the power at port number 3. So first case is if we apply the source at port number 1 and port number 2, and we can see here the phase applied, the input signal is out of phase, means both are in opposite phase. So because we can treat this this boundary as a single boundary of the device, and this one is we can treat as another single boundary of the device. So if the direction of E field is in the upward direction in this arm, and for this arm it is in the downward direction, so at the junction point we have the direction in this way and direction in this way. So at the junction point for this arm, always we arrow touching is this in the direction of always the arrow touching at this boundary. For this case, we can see here the tail of the arrow is touching at this boundary. So always the direction of electric field would be same at this boundary condition. So in this case, again the arrow direction would be like this. So both the electric field direction in the same phase at this auxiliary arm. So in the case of opposite phase, we will have the summation of these two powers. Suppose this one is power P1 and this one is power P2 applied power, and we will get the output of power P3 is equal to P1 plus P2 if we apply the source in the opposite phase. Similarly, if we apply so in that case we can say it is acting as a summation port. Suppose if we apply secondly if we apply the signal in the same phase, like in this fashion. So at the junction point we will have the electric field in this arm in this position, and for this case we will have a electric field direction in this position. So always the boundary condition cannot be changed. So in this condition the arrow always touching at this boundary for this port, and for this port again the boundary condition is same. So we will have the direction of electric field in this way. So clearly we can see here the direction of the field are opposite in the opposite phase in the case of in the case of same phase applied field, so we will have these two fields are cancelled out with each other, so we will have the power. Suppose this one is P1, P2 and P3, so P3 always be equal to P1 minus P2. So if P1 is equal to P2, then in that case we will not have any kind of power ideally. So this is the basic concept of the E-plane T. Now the second case we can see here, if we apply the source at port number 3, what will happen? So if we apply the source at port number 3, so we will get at the junction point we will have the electric field in this position. So at the boundary condition, for this boundary condition, the arrow is touching at this point, so the direction of electric field for this arm would always be in this direction, and the tail is the tail of the arrow is touching at this boundary. So always always the electric field direction would be in this way. So in the case of applied RF signal at port number 3, we will have the power in the opposite phase. So here we can clearly observe here. So this is the case for E-plane T, and this is the structure, 3D structure of E-plane T, and this waveguide, this is main waveguide. This is known as collinear arm, also we can say main waveguide, and this is the side arm that we have attached to the main waveguide. So this is the side arm. Also we can say this is auxiliary arm. And corresponding, if we derive the scattering parameter, so we will have this kind of scattering parameter. So here we can observe here 1 by root 2 and 1 by minus 1 by root 2. Negative sign is representing that this one is in the out of phase. So this is the scattering parameters of the E-plane T. And next is H-plane T. We will discuss it. So in the H-plane, what we have observed in the E-plane T, just we can have complementary nature of the E-plane T in the H-plane, in the case of H-plane T. So in the E-plane T, if we apply the input signal at port number 3, we will have the signal in the out of phase. But in the case of H-plane T, we can clearly observe here the direction of E field always be the same as we have in the case of port number 3. So this is the complementary nature of the E-plane T, and if we derive the scattering parameters, we will have the scattering parameters of the H-plane T. Here we can clearly see here, this is minus sign is not comes into the picture because both the fields in the same phase. Now the next one is Magic Tee. So Magic Tee is nothing but a combination of E-plane T and H-plane T. So we can say this is a hybrid T as well, or EH-plane T as well. Now this is a combination of E-plane T and H-plane T. H-plane T, as we clearly observe here. So it is a its performance will depends on E and HR. So so in the case of if I apply the signal at port number 1 or port number 2, in other words port number 3 and port number 4, so what will happen in that case? So if we apply the signal at port number 3, suppose, so this is a E arm. In other terms, we can say that this E arm is perpendicular to the H arm. So these two ports are cross coupled with each other. So if we apply the some signal at port number 3, we will not get any kind of signal at port number 4 because both are cross coupled with each other. Now the thing is, ideally we can say we have zero power, but practically we will have a very little power at port number 4. So that's why we call the port number 3 and port number 4 are the isolated port. Now if we deliver, if we apply some signal at port number 1 and port number 2 simultaneously, so we will get we will at same phase. Suppose the direction of E field in this way, in this direction, means upward direction, both are in the same phase, so we will get the power at port number 4 because H arm, because in the H arm we will get the direction of received direction of port number 1 is in this way, and from port number 2 again in this way. So both the power will get added at port number 4. So this port we can say as a summation port. Now suppose if we if the power applied at port number 1 and port number 2 are in opposite phase, suppose this one is second case, so in that case in the H arm we will have the direction of electric field in this way, right? From this port direct direction of electric field this one, and for this port the direction of electric field in this arm is, so these two direction of electric field will cancel out with each other. So at last we will not have any kind of power at port number 4 because in that case this port will act as a subtractor port and representation of subtractor port by delta. Now the whatever we have observed in the case of H arm, just we will have the complementary nature at the E arm. Suppose in the same phase this port is acting as a summation port in the summation port, and port number 3 will act as a subtractor port, while in the opposite phase case this port will act as a subtractor port while the port number 3 will act as a summation port. So this is the working mechanism of the Magic Tee. That this is which is nothing but a combination of electric field, E plane T and H plane T. So and these two port are isolated port. These two port are known as isolated port. Port number 3 and port number 4 are the isolated port. So in that case the S43 and S34 would always be equal to 0. Now this is the scattering matrix of the Magic Tee. So this one and this one is the final scattering matrix of Waveguide Magic Tee. Here we can clearly see here this is 1 by root 2. So at this port, at this junction, whenever we apply the power at port number 3, we will have a half power divider as port number 1 and port number 2. Suppose if we apply the power at suppose 6 dB here, we will have in the ideal case 3 dB and 3 dB. This is half power divider. Now the next one is hybrid ring. So this is the structure of hybrid ring. Here we can clearly see here. So this is a 4-port device as we have mentioned here. So port number 1, port number 2, port number 3 and port number 4. Here the distance between the port, means spacing between the port number 1 and port number 4 is 3 lambda p by 4, while rest of the port are kept at a distance of lambda p by 4 respectively. Right now, why we take this distance lambda p by 4 and 3 lambda p by 4? Sorry. Now here lambda p is the guided wavelength, we can say, because this is nothing but a waveguide, circular waveguide, we can say. Suppose if we apply the RF source at port number 1, so we will have two paths at this junction point. Either the power is split in the two directions. This one is anti-clockwise direction, either in direction or in this direction. So at port number 2 we will have the power from this point, from this direction, and from this direction as well. So now we can clearly see here the path difference between these two ports is lambda p by 4, while for this case the path difference is total travel path is 3, 4, 5 lambda p by 4. So if we find the phase corresponding to this path, so we know that path phase difference is equal to 2 pi by lambda into path difference. So this one is 2 pi lambda p and lambda p by 4 cancelled out. So we can say this is pi by 2. We will have a pi by 2 phase difference corresponding to this port with respect to this port, while the same procedure, in the case of 5 lambda p by 4 we will have a multiple of odd multiple of lambda by odd multiple of pi by 2. So we can say at port number 2 we will have the power in the same phase. So we will get the power at port number 2. What will happen if we consider port number 4? Port number 4. Again, for the port number 4, we will have two paths. The first path will be this one, and second path will be this one. And now the total path traveled by the signal is 3 lambda p by 4, while for this again 3 lambda by 4. The same path travel in the both directions, so we will have the power in the same phase. So again we will get the power at port number 4 is the sum of, we can say, suppose this one is P1 and this one is P2, again P1 plus P2, like this way. What will happen at port number 4? At port number 3, so again this is first path, this one is second path. So total path traveled by the signal is RF signal is lambda p by 2. For this case it would be lambda p. Now if we calculate the corresponding phase, the relative phase for lambda p by 2, we will have the phase in opposite direction, in opposite phase, we can say. So we will not have any kind of power at port number 3. No power we can receive. So at last we can conclude here. The adjacent port at port number 1 that is port number 2 and port number 3, port number 4, we will have the power, but the port which is far from the port number 1, that is port number 3, we will not have any kind of power. So similarly for all the ports, we can say for port number 2 we will have the power at port number 1 and port number 3, but we will not have any kind of power at port number 4. Similarly, we can say the other port as well. For port number 3, we can say we will have the power at port number 2 and port number 4, but we will not have any kind of power at port number 1. This is the conclusion of this device. So if we find the scattering parameters, so this is the overall scattering parameter of this device. We can clearly observe here where zero why we mention the 0 for as we discussed, for port number 1 we will not have any kind of power at port number 3. So in that case, port 1 S13 or S31 would always be equal to 0. So similarly, we can, this is the scattering parameters for this device, hybrid rings. Now the directional coupler. Directional coupler is a 4-port device, as we have mentioned clearly here. So this one is the input port, port number 1, port number 2, port number 3 and port number 4. So port number 2 is known as throw port, and port number 3 is known as coupled port, port number 4 is known as isolated port. Why we call throw, coupled and isolated, we will discuss in the next coming slides. So this is we can say this one is a primary waveguide and this one is known as secondary waveguide, right? So always the coupling will happen in first device to second device, that is primary to second, and this is the direct path from port from port number 1 to port number 2, and coupling will always have in the secondary device, that is secondary waveguide. So this one is coupled port. Now coupling so this is a formula for coupling coefficient, directivity, isolation and insertion loss. So coupling always will happen at port number 1 and port number 3. So it is the ratio of P1 divided by P3. Directivity will happen in the in between port number in between port number 3 and port number 4. So directivity is a ratio of port number 3 and port number 4, and port number 1 and port number 4 are the isolated ports. So isolation coefficient will be the ratio of P1 by P4, as we have mentioned here, and insertion loss is the ratio of whatever the power we have given the input and the received at the output. The remaining power is within the device, that is called as the loss, insertion loss, which is defined by P1 by P2, and we have taken the logarithmic of it, so this is in the decimal. Next, two-hole directional coupler. So the mechanism of the directional coupler we can clearly observe, we can clearly understand by looking this diagram. So here we have two holes, the first hole and this one is second hole. So in the case of, if we apply the this is port number 1, port number 2, port number 3 and port number 4, and the spacing between the two holes is twice n plus 1 lambda z by 4. Why we take this dimension here? So because if we calculate the phase difference corresponding or with respect to this length, so we will have a lambda z by we will have the power of we will have pi by 2. So in this case, we can say for delivering the power at port number 2, we will have the addition of the power at port number 4. So and port number 3, the power is cancelled out with each other. That means P1 minus P2. That's why we call this port number 1 and port number 3 is the isolated port. So this is the scattering parameters of the directional coupler. So you can see here. Thank you.